In this section, we will consider the tangent plane as the generalization of tangent line. So let me repeat quickly what we mean by tangent line for a function of one variable. If we have one real function of one real variable, then we can consider the line that is tangent to the graph of the function, assuming the function is nice, that means continuous and has continuous derivative. And the tangent line has the equation y minus y0 is the slope, which is the derivative of f with respect to x at the point x0 times x minus x0. We want the line going through the point x0, fx0 or y0. And this is satisfied because if x is x0, we have 0 on the right, and if y is y0, we have 0 on the left. So this line goes indeed through this point. And we want the slope of the line be equal to the slope of the graph of the function, and this is done by this coefficient. Also, we can consider a directional vector, say with the first component being 1 and the second component being the derivative. So that was easy for one real function of one real argument. And now for a function of two arguments. Now the graph is a two-dimensional surface in a three-dimensional space. So consider one point here, and consider the point x0, y0, and z0 on the surface, on the graph of the function f. Then, if we fix y, then you can think of a plane parallel to the xz plane at the point y is y0. And when we cut the surface, the graph of f, by this plane, then we get a curve, just like a graph or function of one variable, namely x, for fixed y. And we can consider the vector, here it was 1 and f derivative, and here the tangent vector will have the first coordinate 1, that's our choice. The second coordinate will be 0 because y is constant. Now we move in the plane y is constant, so no change in y. And the last coordinate will be the partial derivative of f with respect to x. Or we could assume that x is constant. This time we cut the graph with a plane parallel to the yz plane. And when we take the surface and cut with this plane, we get again one-dimensional curve, similar as before. But this time the independent variable is y for fixed x. And we can also consider the tangent vector. Now x is constant, so no change in the first direction along the first axis. Well, let's assume we can choose the second coordinate to be 1, and the dy will be the last coordinate of this tangent vector. So we have a surface and we have two tangent vectors. So it would be natural to consider the tangent plane generated by these two vectors, these two directional vectors of the plane. And let us describe the plane with the normal vector. Normal is perpendicular to the tangent vectors. And if we have these two vectors, we can find a perpendicular vector by their cross product. So if we take the vector, say 1, 0, fx, and we consider the vector product, the cross product, with the vector 0, 1, fy, then this cross product can be computed using the mnemotechnic help with the determinant I, J, K, 1, 0, fx, 0, 1, fy. So the first coordinate is minus fx. The second coordinate is minus fy. And the last coordinate is 1. Well, I don't like minus, so let's multiply this vector by minus 1, and let's call it the normal vector. Fx, fy, minus 1. And if we have the normal vector of the plane, we can write the equation, namely fx times x plus fy times y minus 1 times z is some constant. And this constant d can be found, can be evaluated, because we want the plane to contain the point x0, y0, z0. So d can be evaluated as fx times x0 plus fy times y0 minus z0. So we have fx times x plus fy times y minus z is equal to fx x0 plus fy y0 minus z0. So this can be written in the form, if we add z and slope left and right, we have z minus z0. And if we subtract fx times x0 and factor out fx, we have fx times x minus x0. Then when we subtract this and factor out fy, we have fy times y minus y0. Well, and this is the equation of the tangent plane. You see, it is similar to this one. This is the dependent variable. It was y for function of one variable, and it is z for function of two variables. Minus the corresponding coordinate at the point of tangency. Here it was minus y0, here we have minus z0. And then we have some coefficient which is equal to the derivative. This is derivative of f with respect to x times x minus x0 times x minus x0. Well, and that's all for the tangent line. And for the tangent plane, we have a similar term like that, just for the other independent variable. Instead of derivative with respect to x, we have derivative with respect to y. And instead of x minus x0, we have y minus y0. And that's all. These two partial derivatives are evaluated at the point of tangency, at the point x0, y0. So this is a constant. not a function. So in a more explicit notation, it would read z minus z0 is. And if you don't like this notation, you can write df dx at the point x0, y0, this is this, times the bracket x minus x0 plus, and if you want to write fy as partial derivative of f with respect to y at the point x0, y0 times y minus y0. It is very important that this derivative is evaluated at this particular fixed point. So all this, although it looks terrible, this is just a number, this is just a constant. And similarly, the partial derivative of f with respect to y is evaluated at the point of tangency. So this is again a number. It may be 0 if the plane is horizontal in this direction. It may be positive or negative, but this is the number, the constant. It's corresponding to the slope of the line. So this is the equation of the tangent plane to the graph of a function of two variables.